Good afternoon, ladies and gentlemen. Welcome to today's Snack and Learn webinar. My name is Jared De Silva. I'm a structural engineer and I form part of the TNI Bridge team in the WSP Bryanston office in Johannesburg, South Africa. Today's Snack and Learn webinar will be about the emergency rehabilitation of this Selby interchange on the M2 in Johannesburg, South Africa. Before we begin, just 2 house rules. There will be a question and answer session at the end of the presentation. So if you do have any questions, put them in the question box on the GoToWebinar control panel. And if you'd like to download the presentation, it is available in the handout box. So just today's agenda for the presentation, we'll look at the background of the project, the key challenges, the temporary works design, the permanent works design, summary of the project, and then our Q&A session. So the project summary, our client was Johannesburg Roads Agency, the JRA. The contractor on the project was Stefanuti Stocks. WSP was appointed by Stefanuti Stocks for the temporary works design, as well as the alternate design for the permanent works. Our team consisted of 3 engineers as well as 2 modelers. The project consisted of 4 mushroom heads that needed to be replaced on the M2 highway. These mushroom type head piers were used due to undermining in the area, and this was due to their suitability to be less affected by settlement. The M2 highway is one of the most used for commuters to get to work in the Joburg area. Therefore, the project was very time sensitive. There was also a lack of stressing bars in the country. So WSP proposed an alternative solution that would be achieved within the needed time frame. Also, the design would not need the stressing bars. So our project takes place in Johannesburg, South Africa. If we zoom in a bit further, we'll see we are in the Joburg area, the Joburg CBD. Zooming in a bit closer, we can see the M2 highway there that is in the red square. These bridges provide access to the commuters in the Joburg area, connecting the east and west of Joburg. The bridge itself is a multi-span simply supported structure made up of drop-in slabs supported by mushroom head piers. Zooming in a bit closer, the repair was only required on the foremost east piers next to the eastern abutment, as we see there in the red square. Looking in at one of our drawings, we can see that it's these 4 mushroom head piers right next to the eastern abutment that needed to be replaced. The drop-in slabs are reinforced concrete and the piers are reinforced with the pre-stressing at the top face of the mushroom head. The bridge has E80 expansion joints and the structure is found on rock with spread footings. We've got a typical elevation of one of the mushroom heads, which are roughly 8 meters tall and 12 by 14 meters in plan. So the main defects on these piers were large shear cracks, as we can see in the images below. The cracks formed due to water entering through the top of the mushroom head and causing an alkali silica reaction. In ASR, the aggregates contain certain forms of silica which will react with alkali hydroxides in concrete to form a gel that swells as it absorbs water. These gels can induce enough expansive pressure to damage the concrete and form these cracks, as we can see. So the key challenges on this project, due to the safety of the travelers, we needed to act quickly in supporting the structure and replacing the piers. But due to how important the highway was to the flow of traffic, the solution also needed to be rapid, introducing our crucial time frame to get the project done. So in order to demolish the existing piers, the drop-in slabs needed to be removed. But due to space limitations in the CBD area, We could not completely remove the slabs, so jacking the slabs up and keeping them in position was the final solution, as we can see in the image below. So to achieve this, we needed to design jacking towers. The loading on these jacking towers was a live load of 0.5 kPa for any workers that would be on top of the decks. The deck weight itself, which was approximately 360 tons, and the steel weight of the structure itself. The drop-in slabs were modeled, and we also used head calculations to determine the loading, and a Procon model was used to design the frame or the jacking tower. Each element was designed in using spreadsheets to optimize the design. Bases were also designed for the towers to stand on to ensure no settlement occurred when the drop-in slabs were jacked. In the design of the jacking towers, a modular design was used, which meant we could use one design to fit most cases with only minor additions. This also allowed for ease of transport, as we can see on the right, how the towers arrived on site, and on the left, we see them being put together for use. This also allowed reuse of these jacking towers for future projects. Adding on to the modular design, we had different types of legs that could be added to the structure to accommodate for the different founding conditions. For the top of the slabs, a 12mm steel plate was bolted to the underside of the deck. The gaps were filled in with an epoxy, and this allowed us to have a flat jacking surface and even distribution of the jacking load. So the jacking procedure, as we can see on the right-hand side there, it consisted of having a packer and the jack next to each other. The jacks were increased at 1.6 millimeters, and every 1.6 mils, a shim was added in so that there was nothing more than 1.6 millimeters of allowable movement if the jack had to fail. Once the jack reached its maximum height, a new packer was added and the jacking continued until the correct height was reached. The jacking height was also monitored daily to ensure that there was no movement in the structure. So this is just a photo of the jacking procedure of one of the drop-in slabs being lifted. Jet demolition was contracted to demolish the piers. Each mushroom head was carefully demolished, and the rubble from that pier would then be used to allow the next head to be demolished. I do have a short video clip here of the demolition taking place. As you can see at the top, we see the stressing bars that were unavailable in the country, leading to the alternate design. The rubble was then removed to ensure a safe working environment, and inspections were done on the jacking towers after the demolition to ensure that there was no damage to the structures themselves. And the bases were also inspected, and it was noted that 3 of the existing bases would be reused and 1 would be rebuilt, as we found cracks in it as well. So as discussed, the alternate solution was due to the time constraints and the lack of stressing bars in the country. And this is where WSP stepped in with the alternate solution to not use the stressing bars and have the design completed within the strict time frame. So the codes that were used in the design of these mushroom heads, we have TMH7 as well as some British standards. The loading comes from TMH7, which we have the NA, NB36 and the NC live loading, as well as the self-weight and the parapets and 100 mils of asphalt on top of the mushroom head. So 3 finite element models were run simultaneously on the piers to constantly review the results and ensure that the results were accurate and making sense. The three packages that we used, we can see here Midas, Strap, and Sumo. Midas and Strap both having very bridge-specific analysis tools, whereas Sumo is a more generic analysis package, and all three of these were used to model the mushroom heads. Just some basic results from the three different packages. We have results from Midas showing the deflection and maximum moments. From Strap, we also have an image of the results of the maximum moments. And from Sumo as well, we have deflection and maximum moments. Just a summary of the results, we have our maximum moments and shears from the three packages. As we can see, the results are quite close, and these results were used for the design of the spreadsheet, design of the mushroom heads. So creep was a very big factor in the design, and to calculate creep of the structure, various conditions needed to be known. So the creep of a structure is affected by various things, such as the average humidity of the area, the shape of the structure, the mixed design of the concrete, as well as the codes being used. So the average yearly humidity of Joburg is 58%. The aggregates used were granites. These were chosen over andesites and quartzites due to its superior creep properties. This information we received from the D2 form from the mixed design of the concrete. So these assumptions were put into Strap and Midas. The results from Strap using the British standard gave us an immediate deflection of 12.7 and a long term of 25.5 millimeters, giving us a total of 38.2 millimeters of deflection. The same inputs were put into our software of Midas, which this one used the Euro code, and it gave us a total creep value of 35.5 millimeters. As we can see, a summary here showing that the results are quite close. The immediate deflection of 12.7 was acceptable, and the deck was pre-cambered by this 12 millimeters to accommodate for this. The long-term creep of 25.5 over the lifespan of the bridge fell within acceptable range, and no further action was needed to be taken. For the column design, the Sumo results differed due to limitations of finding the worst case live load, and therefore the Sumo results were no longer used in the design procedure. NA as well is applied quite conservatively in the Strap model, and therefore we took the Strap and Midas results for the design of the column. So the column was designed using our software packages as well as spreadsheets, and it sits at 71% utilization with 2 layers of Y20s around the column. Another aspect that was very important for this design was the half joint where the drop-in slabs would sit. To design this half joint, a strut-in-time method was used. So we took the reactions from the drop-in slabs, approximately 440 kilonewtons, and we took moments about a crack line at the back here using the strut-in-time method. We were able to quantify the forces in the horizontal rebar, the vertical rebar, and the diagonal rebar. So after the design, we noted that we needed additional Y20 diagonal bars in the half joint itself. So here we can see the final solution. We've got a 3D rendering of one of the mushroom heads, as well as our 2D drawings of the mushroom head and our half joint detail. For the columns, the final solution to tie into the existing bases, we decided to use splicers, couplers, as well as chemical anchors. And we can see the 3 different solutions used. So the chemical anchors would tie into the concrete, being chemically anchored into there. We used the mechanical anchors to tie into the existing starter bars from the base, as well as splicers. And all of these 3 anchoring solutions were put at different levels to avoid any plane of failure. So these are just some photos of the construction of the column. We can see the existing starter bars there from the existing base. And here's a photo of the finalized column, as well as the formwork being put in place for the mushroom head itself and the starter bars sticking out. For the mushroom head itself, due to the complex geometry, it put a lot of strain on our drafting team to get this rebar out within the small time frame, but it was completed. And an additional note was that we put in a cage inside the mushroom head. Because it being so thick, we added this additional cage to accommodate for any thermal stresses inside the head itself. And we've also got our detail of the half joint rebar. Just some photos of the construction of the mushroom head. We've got the formwork being put in place on the right, and on the left we've got the rebar being fixed into position. Just some additional photos of the rebar being fixed. On the right here we have our half joint rebar being fixed in place, and on the left we have the top reinforcement, which was bundled Y32s. And here we have a photo of the final mushroom head with the drop-in slabs being dropped into place just on time for us to open the highway to the public. During the project, there were some sustainable development goals that we achieved. Number one, we can see no poverty. So in the construction, we were able to utilize some people in the area, enabling us to train these people with skills that would be able to better their futures, as well as point number 8, decent work and economic growth. So obviously keeping the highway open and having it have a longer lifespan would be sustainable for the future of economic growth. In summary, the project started in December 2018. The temporary supports were completed in February 2019, and the decks were jacked and the piers demolished in May 2019. The mushroom heads were completed at the end of October 2019, and the bridge was open to the public and has been opened since. We now move over to our question and answer session, in which Johnny Stradom is the technical director, will join me to answer some questions.
Thank you, Jaron, for a fantastic presentation. So just a reminder, before moving into the Q&A period, you can log your questions in the question box on the GoToWebinar platform, and also you can download the PDF version of this presentation in the handout box on the dashboard. I will start with the first question. What is the design life of the structure? Is it for 100 years, and is it only the new refurbished section?
So that is correct. The design life of the structure is 100 years, and it is only for the 4 mushroom heads that were built.
Thank you. Next question is, any structural health monitoring is being carried out during and after rehabilitation of the bridge?
So we did survey the drop-in slabs, and they were monitored throughout the construction stage to determine if there was any settlement or movement of the slabs. And we also asked that the structure be surveyed every few months after construction so that we could ensure that the creep results that we got were correct.
Fantastic, thank you. Was any additional work done to the existing bases?
The existing bases were inspected, and there was no additional work done except for the fact that we put carbon fiber around the column to strengthen the bottom section of the column stub. So that was the only additional work that was done.
Thank you. How did you know what piers were found on?
So we had a geotechnical investigation done, which It then gave us the answer that it was found on rock.
Fantastic. There's a question here. How did the construction impact traffic closures? And also, were consideration made with the proposed concrete design mix to ensure that the future ASR would not occur?
So for the concrete mix, as mentioned, we did use aggregates that were a lot better in terms of creep. So obviously with the less creep, the less deflection we would have, and the less likely we would have this ASR reaction happening again. If you could just repeat the first part of the question.
Sure. How did the construction impact traffic closures?
So it was impacted quite severely, as noted in the beginning. This highway is very frequently used, and that's why there was such a crucial time frame on us getting the highway back open to the public.
Thank you. Next question is, where did risk contingency play a major part, and in what category? Is it financial risk, operational risk, or reputational risk?
I think the main risk was just completing the design within the allotted time frame. So that's where majority of the risk was coming from.
Fantastic. From a seismic point of view, how is the behavior of the mushroom head pier? I'm not sure I understand this question. Speaking about seismic point of view for this bridge.
Okay, so because the area itself is already undermined, we expect some sort of movement, and these mushroom heads, because they simply support and quite wide spanning, it's quite accommodating to slight amount of movement. So that's why these mushroom heads are used in these areas.
Thank you. Were any of the steel jacking structures damaged during demolition? And if not, how did you prevent this?
So none of the structures were damaged. We did inspect them afterwards. We did a thorough inspection on all of them to see if there was any damage. What we did do is we had barriers along the side of the jacking towers, so that as the heads were being demolished, none of the rubble would fall and hit into the structure. We also asked the contractor, Jet Demolition, to obviously take care when they were on the close edge or near the jacking towers.
Thank you. I have a lot of questions. Next one is there any requirement for the design of the slab sit geometry for earthquake loads in the location of the bridge?
Not necessarily, again, due to the size of the structure and the reasons that they are used, there's not much need for any geometric changes to the structure. So the mushroom head itself makes it quite a stable structure.
Thank you. Another question is, in terms of health and safety, was any major incidents reported during construction and while the decks were in the jacked position?
No, there were no incidents. The jacking itself went quite smoothly, and there was no incidents reported during the jacking or after. And maybe just a note on the previous question as well, we did apply seismic loading to the models as well. So this was accounted for in the design.
Fantastic, thank you. We don't have additional questions. I think we had quite a lot. So looks like we're at the end of the webinar session. Please feel free to follow up directly with Jared for any additional questions via the contact details shown on the screen. And I would like to thank Jared for a fantastic presentation. Thank you very much. And thank you, Johnny, for your support. And thank you for all attendees for joining today and joining the 2021 Snack Along webinar series. Thank you, Jared. I will wrap up the webinar now. Thank you.
Thank you.